But today I would like to share a different story with you. Also short service announcement. I'll be looking at my phone every now and then. That's not just to keep track of time, but there's also a non-zero chance that my wife will give birth. So if you see me running away all of a sudden, you know why. So back to chemistry. Today I would like to share with you a tale of two coppers, but also some hydrides and some alkyls, because I got some exciting results from my student the other week, which I also decided to include in the talk of today. And basically what I'm going to be talking about is how we can use expanded pincer ligands, how to probe and modify the inherent reactivity of robust di-copper complexes. So many of us here in the room work in homogeneous catalysis or organic synthesis. So we always like to think, how can we rationally modify the transition metal catalyst that we have? We often have ligands, we have a vacant site, and some additional factors. So one way we can change the gears of our catalytic system is by changing the metals, changing the oxidation state, thereby altering the electron density available on the metal. Or we can change the ligands, change the coordination type, perhaps introduce some fancy redox non-innocent ligands, or ligands that have the ability to help out with making and breaking chemical bonds, in, for example, metal-ligand cooperativity. Or we can change the reaction conditions the most simple way. We can change the solvent, change the temperature, and thereby affect parameters such as yield, turnover frequency, etc. However, something that's not often considered is how many metals do I have in my catalytic active site. And that's something that I'm very interested in and plays a big role in a lot of chemical transformations. And I would like to start by giving you an example for the work involving copper hydrides. Copper hydrides are widely applied in organic synthesis, and here you see how they are generally synthesized. We take a copper halide source, usually with a ligand already attached or a ligand that we add as well, and we add a hydride source. It can be an alkali metal hydride, can be hydrogen gas, or a borohydride, for example, and subsequently we displace the halide and make a copper hydride. The most famous example of such a copper hydride, which is made in a similar way, actually doesn't form a well-defined mononuclear copper hydride, but it forms a hexanuclear copper hydride, which is also widely known as Stryker's reagent. A Stryker's reagent is a very powerful tool in making or functionalizing molecules, especially if you would take a classical sodium borohydride or lithium aluminum hydride and you react it with this enone, what you would reduce the ketone to an alcohol. However, if you use a more softer hydride in the form of a copper hydride, what you actually get is you get selective reduction of the alkene inside this molecule. And in addition, Stryker's reagent is also widely employed in hydrosilylation. So reductive hydrosilylation of ketones, add a silane, a very tiny amount of the Stryker's reagents, and you can make the siloether, which you can subsequently hydrolyze to the alcohol. And a variety of enantioselective transformations have also been developed on there, but that's not what I'm going to talk about. Because what I would like to focus on today is fluxionality. So fluxionality, when you make such a copper hydride in situ, this copper hydride is not very happy because transition metals like to have 18 valence electrons, and if we have a 2-electron donor here in a hydride, we end up with 14 because copper is D10. So what copper hydrides typically tend to do is they tend to aggregate through multi-center 2-electron bonding. So for example, this copper hydride can dimerize, where you have now 2 bridging hydrides. However, you can also trimerize, where we now have 3 bridging hydrides. Add another copper, we have a tetranuclear cluster, and then the hydrides don't necessarily need to be on the edges, but they can also be on top of the surface, where they are bound to 4 different hydrides. Or we can end up with a situation as we just saw in Stryker's reagents. As you can see, we have a variety of possible aggregation states. However, it is very difficult to rationally control these, because in solution, when you change the conditions, they might just simply be all present at the same time, or you might be in a favorable scenario over here. But when you do a catalytic reaction, you're not at a steady state. Your substrate concentration will slowly deplete and you might form a new product, which can also completely alter which aggregation state you are in. Moreover, it doesn't stop at 6. And I would like to show that by a really intriguing example, I would say, is these gigantic copper hydride clusters that have been reported by the group of Liu and Sayar, where they take this dithiophosphonates and they do a reaction just like I showed you. Take a copper halide or take another copper precursor, add a hydride source, and they get these copper hydride clusters with 30 coppers in there. If you change the ligand from a dithiophosphonate to a dithiocarbamate, you end up with 28 coppers in there. If you subsequently add a reagent, such as an alkyne, a terminal alkyne widely used in copper catalysis, you reduce the cluster size approximately by half, and you get 15 coppers in there. And you also have terminal alkynes or acetylides bound mu3 to 3 coppers at various positions in the cluster. When you make this compound, it actually isn't very selective, because if you take a look at this line or this section from the original paper, when they tried to make this, it's only forming 20% yield, and you also form an octa copper cluster. Dissolve it in dichloromethane, and you lose 2 more coppers. So how do you study a catalytic reaction when you have so much variation in aggregation and surface facets? Quite a challenge. So typically what we do is we add very sterically bulky ligands. And these are some of the really state-of-the-art copper hydride systems where we have a copper hydride with a bulky and heterocyclic carbene ligand. And Bullock, a couple of years ago, reported actually that these systems are fluxional in solution, and that actually all the potent insertion chemistry is actually happening with the mononuclear systems. So how do you then study actually what the intrinsic reactivity of the larger clusters are? So multinucleating ligands are a strategy that is being pursued towards this end. And here you see a tetradentate ligand where the tetranitrogen fragment sort of sticks onto the cluster like sticky tape, which provides higher stability in solution and also a more robust copper hydride cluster. However, as you can see, changing the solvent makes you lose an additional copper atom. So they're still sensitive to changes in aggregation state in solution. So how do we then get to cluster structure activity relationships? How do we probe the inherent reactivity of these smaller clusters, but also of the various surface facets that we have in these clusters? To do so, we need robust copper hydride clusters of low nuclearity. So if we take a look at the same cluster that we just saw, I just blew it up a little bit. What the ligand is actually doing, it is nicely binding to 4 individual copper centers with each nitrogen atom. However, the ligand has a large open face, so it doesn't prevent more coppers or more ligands coming in. Naphthyridines have a very similar binding motif and is a molecule that we are working a lot with in my research group. And here you see another example of a tetracopper chain that is stabilized by 4 or by 2 naphthyridine-derived ligands, where we have 4 alternating nitrogen-carbon fragments, similar to what we have here. However, if we want to prevent this aggregation, we need to actually cap the naphthyridine by basically preventing additional copper fragments from coming in or from additional ligands, to thereby really make robust, well-defined di-copper systems. So these ligands are not new. People have been working on them for quite some time. And here you see some examples. For example, this trispyridyl fragment that makes these well-defined bimetallic complexes that we'll see appear a few times throughout the lecture. These diimines that have been worked on by Broere and Ueda and also by us in some unpublished work. We have these pyridine-derived ligands, these really old systems that have been mainly studied in the context of mimicking or bioinorganic chemistry in multimetallic active sites that we recently also published some electrocatalytic oxygen reduction reaction, which I won't talk about today. Because today I would like to mainly focus on these PNNP expanded pincer ligands that were developed by my group and also recently adopted by the Holger Braunschweig group in Germany. So here you see a key element of these ligands. We call them expanded pincer ligands because they're similar to the classical expand or normal pincer ligands, but we expanded the binding pocket to accommodate 2 individual metal sites in close proximity. And they are inspired or designed basically to have this 1,8 naphthyridine fragment, but also these P, C, or the methylene linkers adjacent to the heterocycle, which have been, are well studied for metal ligand cooperative bond activation, as you can see here with these P and P mononuclear fragments. And what that does, as soon as you deprotonate one of the methylene linkers, you get this nucleophilic methine fragment that can cooperatively activate chemical bonds, whereby the electrophilic fragment ends up in the methylene linker and the nucleophilic fragment ends up at the metal site. We have 2 of those systems. Perhaps that can also play a role, and we'll also see later today. But the main thing that we'll talk about today is how can we use these systems to stabilize well-defined di-copper fragments. So first, we have to bind the copper into the ligand system. And this is also, as I showed 2 weeks ago, but I'd like to repeat it because it's going to come back a few times today. So if we react our expanded pincer ligand with 2 equivalents of copper chloride, we nicely get this dicopper chloride. The NMR spectrum is what you expect, C2V symmetric species, so 1, 2 distinct naphthyridine protons that you nicely see in the NMR spectrum. If we deprotonate this, we partially dearomatize the naphthyridine core, we lose the C2V symmetry, and we now get 1, 2, 3, 4 distinct resonances. And if we do that again, we again regain the C2V symmetry. We see 2 resonances appear again, but as you can also see, as we are dearomatizing the naphthyridine core, we also see an upfield shift showing that we need to lose some of the aromatic character of the ligand system. Well, here we can use potassium T-butoxide. Here I schematically depict it as losing a proton, because it really depends on what transition metal you bind there to see what type of base you need. In this case, we actually used benzyl potassium. Benzyl potassium is basically deprotonated toluene. And if toluene is your conjugated acid, it tells you a bit of how strong of a base this is. But with other metal centers, we can also use milder bases. But once we had access to our fully dearomatized PNMP dicopper system, since we were inspired by the metal ligand cooperative design of the normal PNP pincer system, we were wondering, can we do metal ligand cooperative bond activation? And one of the most classical reactions to study is cooperatively activating dihydrogen. So normal copper systems don't do this. Also with sort of half of the ligand, what you see here, so mononuclear analogs of what you see here. And this is the reaction we imagined. So we add dihydrogen, we lose potassium T-butoxide, and 1 hydrogen ends up on the methine arm as a proton, and we get a hydride between the dicopper systems. So when we exposed our mixture to dihydrogen, what we saw is full conversion to a new species that indeed had all the distinct features what we would expect, or most of them. So indeed we see 1, 2, 3, 4 naphthyridine resonances, so we lose the symmetry in the naphthyridine backbone as we see here. And we see a methine linker integrating for 1 proton, which is the star over here. But the methylene linker, so the CH2 group over here, showed some unusual behavior, at least unusual from what we would expect. Moreover, we didn't see any hydride resonance, because here the methylene linker splits up into 2 individual protons that are clearly chemically inequivalent. And took us a long time to figure out what actually was going on until we got a crystal structure where it actually showed that we get a dimerized structure, where 2 of the copper hydride fragments, as we've drawn them here, basically add together. And here you see that depicted. And if you look at the tetra copper core, we actually have a sort of butterfly-shaped tetra copper cluster with 2 hydrides, mu3 bound, that are sort of capping the surface of the butterfly. And we could also find the hydride location in the Fourier difference map and by DFT calculations that basically show that if we optimize the geometry of a system like this, it looks quite reasonable. So we still didn't see the hydride, and the answer came to us when we started doing isotopic labeling. So when we do a reaction with D2, we indeed see that we include deuterium in the methylene linkers, but we could also independently synthesize this compound by taking the partially dearomatized analogous complex and reacting it with a silane where we formed the siloether and also this hydride. And that way we could actually selectively deuterate at the copper deuteride phase. And then we found with deuterium NMR that the deuterium is actually at plus 1.2 ppm, which is something that I completely did not expect, because I've been doing a lot of transition metal catalysis and coordination chemistry, and always hydrides are between 0 and minus 40 ppm. And the reason we didn't see it in this compound is because these T-butyl groups are also at 1.2 ppm. So a difference of 1 proton with, let me see, 36 protons is really difficult to see, especially since relaxation times usually play a bit of a funky role there. So now I've been doing a lot more of this chemistry. It's actually well known that copper hydride clusters show hydrides at positive chemical shifts. And actually, depending on how the larger your cluster gets, the more downfield it shifts to higher ppm values. But at the time, we didn't notice. Something else that we found that was never published, but I would like to share with you today, because I'd like to share a lot of unpublished stuff today and see if they perhaps get some feedback whether it actually makes sense or not. But here is something, we see the same compound as on the previous slide. So this is what we did the cooperative hydrogen activation with. We formed a tetracopper hydride cluster. But what we noticed when we, instead of having a THF solvated potassium, we add a crown ether, we saw that the chemical shifts in the NMR spectrum looked a bit different. Not very different, but subtly different. But when we then did the reaction with dihydrogen, we saw that this reaction was much faster than when we have a crown ether around. So to us, that suggested some involvement of the potassium ion. In other words, this gave us an excuse to look at other alkali metals. And since we make this compound with benzyl potassium, we got to play with elemental cesium and rubidium, and we made the sodium, potassium, rubidium, and cesium equivalents thereof. So my PhD student, or actually it was a master student, who was very excited that he got to do these experiments. And indeed, when we then look at the rate of the various alkali cation derivatives, we see a distinct effect on the rate of the reaction. However, the reason that this is unpublished is because we cannot reproduce this. We can reproduce this, that there's a distinct effect, but every time we get a different plot. So, and that is because these compounds are so incredibly sensitive, and this cooperative hydrogen activation is so sensitive to really tiny impurities that different batches of compounds basically give very different kinetic plots. So this will likely forever be unpublished, because I had a really experienced graduate student try to reproduce this. He reproduced it the first time, but not the second time. Then the third time it worked again. So we decided this will just be for presentations. But the previous story we were really excited about. And at the time, Erikos was the only master student in my group. I didn't have any PhD students at the time. But since we were both super excited, and some other of my colleagues also, we decided to submit it to Angewandte Chemie. Well, reviewer 1 loved the work. Reviewer 2 said, well, great work, but you need to do some cool catalysis with it. But since half of my group at the time went for a 6-month internship with Ian Tonks at the University of Minnesota, that didn't work. We tried a few things, but basically we didn't have any manpower to do the experiments suggested by the reviewer. But they also offered us a transfer option to Chemistry European Journal. But that copper hydride catalysis, that comment from reviewer 2, always stuck in the back of my mind. So after a couple of years, we decided to revisit this. And what we found the previous times is that copper hydrides, they're well known in homogeneous catalysis. We know how they are made, but low nuclearity copper hydrides, so clusters with less than 5 hydrides, are very rare. And they're well known to be very potent in hydride insertion chemistry. And here you see one of the state-of-the-art systems. Well, this is already from 2013, but basically systems that look like this are really sort of the state-of-the-art in copper hydride catalysis. And they are really characterized by a very significant negative charge that they on the hydride, so they readily react with acids. They insert into pretty much every unsaturated chemical bonds, alkenes, alkynes, and they're also widely applied for hydrofunctionation reactions of unsaturated bonds, especially hydrosilylation. So we made a fancy ligand, we made a fancy dicopper hydride, and then we thought, well, do some fancy catalysis. However, that turned out not to work because our compound turned out to be an absolute brick. It didn't react with anything. No unsaturated molecule that all low nuclearity copper hydrides were supposed to react with. It didn't just sat there, looked at it, nothing happened. And if you look at the space filling model, you actually can figure out why. If you look at all these hydrogen atoms in white, you see basically a tiny shade of white in the middle there, and that is the hydride. So you're basically completely blocking off that copper hydride, preventing any reaction. So in, what was it, I think 3.5 years ago, I had a very good PhD student starting my group, Broere Bieneman, and I asked, can you think of a way how to break up this dimer and get copper hydride catalysis? So together we came up with the following idea. Since we have this expanded pincer ligand, which changes its rigidity but also its charge as a function of its protonation state, we thought, oh, here we have a neutral system. What if we protonate it or deprotonate it? We change the rigidity. Maybe this dinuclear or dimeric aggregate cannot form anymore, but we also can generate charge, and maybe Coulombic repulsion will push the two halves away from each other. So together with a German master student, Alexandra Schanz, we first looked at protonating the cluster. Well, we can make the monocationic cluster, we can make the dicationic cluster, and then the proton ends up on the methylene linker over here and over there. However, both in the solid state as well as in the solution, we showed that these are still dimers. So what about deprotonating it? Well, after quite some time, we found that if you use potassium T-butoxide and 18-chrome-6, very important. Without 18-chrome-6, nothing happens. But with 18-chrome-6, you sort of sequester the potassium ion, making it a much stronger base. We can get this well-defined anionic dicopper hydride. And this is actually the first structurally characterized dicopper or anionic dicopper hydride in the literature. And it just looks really cool. We're really excited about this molecule. It's probably one of my favorite crystal structures in the group. However, what I just told you is that low nuclearity copper hydrides are very hydridic. They react with alcohols to form hydrogen gas. But if you look at the synthesis scheme, we're making an alcohol. So that was the first alarm bell that something is strange. Moreover, same reactivity as the previous compounds. Alkenes, alkynes, even imines, no reaction. So that got us puzzling a bit. And when nothing else works, you usually go to hydrocyanidation. So I had a bachelor student visiting my group for 2 months. She was doing her bachelor thesis, Pascal Ohms, and she figured out that this compound indeed does hydrocyanidation. It's not a very practical case because it's very sensitive, but if you look at the space filling model of our anionic dicopper hydride, you can see that that hydride is really exposed, so sterics cannot be the problem. And we figured perhaps because we have such a large dinuclear active site, we can use very large bulky substrates. So we took diphenylketone or acetophenone, or benzophenone, sorry, with triphenylsilane, and we found that with only 1% of catalyst at room temperature, basically we get full conversion before we reach the NMR. And if we really slow it down for comparison, we can see that we have a significantly higher turnover frequency than a mononuclear analog, and this PNP pincer doesn't do any catalysis whatsoever. So with reviewer 2 from the previous time in our mind, we thought, hey, now we got some catalysis. Let's just show that this is indeed going via a hydride insertion mechanism, since we're talking about hydrides. So if you look at the classical mechanism of ketone hydrocyanidation, we have a copper hydride, you add a ketone, it inserts to form this alkoxide, then a silane comes in, and subsequently via a concerted pathway, you make the silyl ether and you reform the copper hydride. We thought, easy. We just need to prove that we have hydride insertion. So we took our copper hydride, we added 1 equivalent or an excess of the ketone, and we saw no reaction happening. No changes in NMR, but at large excesses we did see some slight shifts in some of the resonances, but basically nothing happening. But because we did see a tiny shift, we thought perhaps we're dealing with an endergonic uphill equilibrium, where the Insertion product is slightly uphill. It is very accessible, but due to the difference in free energy, you don't see it. So, according to the microscopic principle this principle of microscopic reversibility, if that is the case, if we would make this species over here, it should readily convert back to the copper hydride. So we spent quite some time making the same compound with a beta hydrogen atom over there. So we figured, well, this should easily do the beta hydrogen elimination, release the ketone, and reform the copper hydride. But it was stable as a brick. No beta hydrogen elimination was observed. So we don't have an endergonic equilibrium step. At that point, we thought, let's just try isotopic labeling to see what is going on. So if we isotopically label the hydride over here, or don't isotopically label it, but add a silane, the hydride should do the insertion, end up at the beta position, and then basically in this intermediate still be over there, and then end up in the ketone, whereas the hydrogen atom should then end up back over there. So we did a single turnover experiment where we didn't isotopically label the catalyst, we used a deuterated silane. So we mix the anionic copper hydride with the ketone, then add the silane, and what we see is that we have no or practically no hydride incorporation into the substrate, which shows us that we don't have any hydride insertion. The 4% or the 6% that we do see is actually due to scrambling, because if we mix the hydride with the silane at a roughly slightly slower time scale, we also see scrambling going on. But this showed us that there's no hydride insertion. So our leading hypothesis for a long time was, hey, we have a nice low nuclear dicopper hydride. And according to what was known in the field, low nuclearity results in very potent hydride insertion chemistry. However, we found that these systems are nothing alike. They don't react with weak acids. We don't have any insertion chemistry. It does do hydrosilylation, but it doesn't go via hydride insertion mechanism. And if you look at all these characteristics that I've listed here, that is basically what Stryker's reagent embodies. That also doesn't react with acids, doesn't do hydride insertion into a variety of unsaturated bonds. It does do hydrosilylation, but it's also been shown not to go via hydride insertion. So in other words, our dicopper hydride reacts like a larger cluster, showing that there's actually more to the intrinsic reactivity of low nuclear hydrides than having low nuclearity alone. But it's still hydride. Some more unpublished work over here. If we react it with 2 equivalent of a hydride abstractor, it also works with 1 equivalent, but because the reaction is a bit messy, it goes cleaner with 2 equivalents. We can still abstract a hydride, forming the triphenyl borohydride and this really wacky compound over here, where we basically have 4 copper atoms with 1 hydrogen in the middle. So we couldn't actually locate the hydrogen atom here using X-ray crystallography, but computational models place it in the dead center of those 4 copper hydrides. So to the best of my knowledge, nothing like this is known in the literature, but this is something we're still working on. And probably it's also not very reactive because that hydride again is really blocked in by all the steric bulk of the ligand system. So let's take a step back. Let's again visit low nuclearity copper hydrides. The common reactivity, as I mentioned, of copper hydrides is that they insert into unsaturated bonds. And well, nowadays there's a lot of interest in doing CO2 functionalization, and indeed most well-defined low nuclearity copper hydrides, such as the ones that I showed before, or a neutral analog with 2 hydrides, this example here from Ken Carlton or from Tenace, indeed all show this distinct reactivity. You have a copper hydride, you add CO2, you basically do form and you generate a formate via a hydride insertion pathway. And subsequently, you can hydrosilylate CO2 to form siloethers. Some unusual reactivity for a few copper hydrides that has been reported has also been reported by Tenace. Here, you see basically the same ligand system as on the previous slide. So a multidentate phosphine ligand, but instead of a single CH2, we now have 1, 2, 3, 4 CH2s. And that forms a slightly different cluster And when they add CO2 to that, they get hydride insertion. But unlike all other known cases, it is reversible. So when they remove the CO2 atmosphere, they go back to this funky copper hydride. Another case reported by the Tilly group is of these copper hydride clusters. So unlike the systems that we reported, they still need to aggregate with additional copper atoms which mysteriously appear throughout the reaction. So it's not a very clean reaction. And although this doesn't react with CO2, it is a catalyst for the formic acid dehydrogenation pathway. However, both systems don't really show great catalytic activity, and also there's little or no mechanistic insight due to stability issues of the systems that they work with. So we thought, let's try our systems. So we take our dinuclear or dicopper hydride, and surprise, surprise, when we add formic acid, what do we form? Our brick. Well, not very surprising, because we make it by deprotonation from this compound. So, but when we then add an excess of formic acid, something happens. In THF we get a precipitate, but in acetonitrile we get a nice solution. And when we look at that solution by NMR, we see a C2V symmetric species forming. We seem to have a neutral PNMP ligand, suggesting that these methane linkers are protonated. And there's a broad resonance at 10 ppm that every time we measure is at a different spot. Well, we were able to grow some single crystals of this, and we have, I would say, record-breaking ellipsoids on there. But that's the best that we can do, because there's a lot of disorder in the formate molecules. And what it actually looks like in a ChemDraw representation is we have indeed a protonated PNMP expanded pincer ligand with two bridging formate ligands over there. And we now know what's going on with that broad resonance, is because if you wait long enough, it returns to our brick. So even if you have an excess formic acid around, we lose H2 and CO2, and we reform our brick in the end. And that resonance keeps on moving because it is dependent on the formic acid concentration. So if you have a lot of formic acid around, the resonance is at where you would expect formic acid, but as the reaction progresses, it slowly moves towards the formate complex. And once we have the formate complex, that does another formic acid dehydrogenation to make the tetra copper dihydride that we have. A headspace GC analysis shows that we only form CO2 and hydrogen and no CO. Since our system was so well behaved, we thought, this might be interesting to gain some mechanistic insights into why it displays this reactivity so unlike normal copper hydrides. So for that, we built a nice inline GC setup. Because this chemistry is quite sensitive, we use J-Young NMR tubes because we got the best reproducibility with that. We can also use larger vessels, but reproducibility seemed to be a bit more tricky there because of small leaks. We have an N2 carrier gas that basically flows over the headspace of this NMR tube and then basically flows the gas mixture of the headspace into the GC. And here you see a typical raw data that comes out of the measurement. We have an equilibration period where we're sort of replacing the nitrogen for hydrogen. Then we have a stable period, and then the reaction is over and we slowly start to lose our dihydrogen. And from here, we get most of our useful information. And for those of you who have a keen eye, you can already spot something is weird about this, but we'll get back to that later. And nicely what we see, when we start off, we have the red color of our hydride, then of our formate species, and as we progress after the reaction is over, we form our hydride species back. So if we do kinetics, we look at the catalyst concentration, nothing strange is going on. We see a linear plot when we plot the natural logarithm of the reaction rate versus the catalyst concentration, showing that we have a first order in catalyst. But when we look at the effect of the formic acid dehydrogenation, we see something unusual or that we didn't expect. We actually see that the substrate, formic acid, inhibits the reaction. That is also very clear when you look at the kinetic traces. Here you see if we go to higher concentration, we see that the rate of hydrogen generation reduces. And if you look at an individual profile, you see that as the reaction progresses, the formic acid concentration decreases and the rate starts to increase. And that's also what we see here, because if you would have a stable catalyst, you would expect a flat slope that at one point sort of dies down. But what you see here is that the concentration of hydrogen increases in time, showing that the reaction keeps on going faster and faster. And from this we could derive a relatively simple rate law, that we have a first order in the catalyst and a negative first order in formic acid. I'll get back to that, so I'm just going to park that elephant in the room over here for now. So first we were looking at the kinetic isotope effect. What is going on here? So if we take formic acid, here we've done the reaction in triplicate. So you see there's some variation in the data, but it seems to be rather consistent. If we then use deuterated formic acid, where we selectively put a deuterium on the carbon, we see that the reaction slows down, which indeed is very consistent with the rate determining step being the beta hydrogen elimination. So we have a kinetic isotope effect of 3.4 for the CH bond, which is very similar to other formic acid dehydrogenation catalysts. However, something strange happens when we use the di-deuterated formic acid. So we have a deuterium on the carbon, but also an O deuterium bond. In that case, we see that the reaction is faster than the monodeuterated formic acid, but still slower than that. And we think that is due to a combination of a kinetic isotope effect on the carbon deuterium bond, which slows the reaction down, but the OD actually makes the reaction faster. And that is because we think there's an equilibrium isotope effect that is also consistent with the negative first order in the reaction. So this is the current mechanistic proposal. There's still a lot of uncertainties, but when we take our brick, we add formic acid, we know we get to this diformate species, which seems to be the resting state of the reaction. Subsequently, we do a beta hydrogen elimination to release CO2, form a hydride. Subsequently, that can release dihydrogen cooperatively with the methionine linker to form a monoformate species, or alternatively, it reacts with formic acid to form dihydrogen and also regain species 2. And we think that there's an inhibiting pre-equilibrium with an off-cycle species right before the rate determining step over here, which is where we think the elephant is coming from, and why we have a negative equilibrium isotope effect, that if you have a deuterated formic acid, you push the equilibrium over here, which has been known for pre-equilibrium isotope effects. But this is still a work in progress. Let's see how long I've been talking to you already. So that should be 40 or so minutes. Let me quickly wrap up the last part, and I would like to quickly shift gears from copper hydride chemistry to organocopper chemistry. So basically, same stuff. If you take a Grignard, you do nucleophilic addition on the ketone, make an organocopper or a cuprate, and you get 1,4 addition. I'll skip this, but basically we have the same complications as for copper hydrides. You get aggregations, various aggregation states, and we've also been able to make some well-defined copper systems, but I'll skip to that. Because this is the stuff that has come in last week that I'm really excited about, is looking at the copper catalyzed azide alkyne click reaction, a reaction that I think needs no introduction given the fact that it won the Nobel Prize last year, but copper acetylides like these are also known to aggregate. For example, this one that I showed to you in the introduction. So that makes it very difficult to do mechanistic studies. But experimental and computational studies have shown that dicopper species, or a second copper in close proximity, hanging around, activating the alkyne, also to form this intermediate, can be beneficial. So this is something that I will also quickly skip, because the Tilly group has done some work on this already, basically showing indeed that you can have a well-defined dicopper acetylide to do subsequently the dipolar cycloaddition to form a triazolide species, which can then react with an alkyne again to reform this system. And some computational work by the Balcells group actually indeed showed what is already well known in literature, that if you take a system that is derived from this, which has not been experimentally reported, that the rate determining step of the reaction is basically transfer of the proton of the alkyne to the triazolide. So since we have a metal ligand cooperative step, we thought we can have some benefit therein. Moreover, in some work that we recently published, where we sort of look at steric quantification of the dinuclear active site, we show that our systems are less bulky than the Tilly group. So we thought perhaps this would be beneficial for this click reaction. So using some mesotyl copper complexes that we made before, we can indeed gain access to these well-defined dicopper acetylides. Although we can't crystallize it with the isopropyl groups, if we substitute for T-butyl groups and we have a slightly different alkyne, we were able to crystallize it and got a solid state structure, and all the NMR data suggests that we indeed have this in solution. However, this is not stable, because in time, especially if you heat it in hexane, we get this really unusual tricopper acetylide, which is also a really funky structure over here. We have basically 2 PNMP ligands that are bound to 3 individual copper, so we lost the copper along the way. And this is something that, according to the crystallographic database, is not known at all, where we have a acetylide that basically is bound to 1, 2, 3 copper systems. It's quite a unique system, but it's a decomposition product, so we can now make it rationally, but that's not really what we're aiming at, because what we were going for is showing, can we indeed do click chemistry with these? And indeed, what we found, when we add the azide to the acetylide complexes, we do the dipolar cycloaddition, we make the triazolide complexes, and whereas the Tilly group system actually needed some heating and long reaction times, our system at room temperature, which is obviously somewhat different, goes to full conversion within 2 hours at room temperature. And I'll skip the NMR characterization because that's quite a pain in the ass to go through. But here we see that we indeed have a solid state structure. And the one thing I would like to point out from the NMR spectrum is that this system is basically, you have a dicopper naphthyridine, we have a triazole bound orthogonal to it, and the only difference on the top and below the plane is that we here have a nitrogen atom that is sp2 hybridized and there a carbon atom. And that subtle difference makes a huge difference in the NMR spectrum, because we get a forest of isopropyl groups, because every isopropyl group experiences a slightly different magnetic environment, and we get some really funky coupling complexes. But what I was really interested in and is, can we do metal ligand cooperative proto-demethylation, which is basically always the rate determining step in these systems. So if we add our, or take our dicopper triazolide and we add an alkyne in THF room temperature overnight, we get full conversion to our dicopper acetylide and we release our triazole. If we monitor this spectroscopically, we see a species that is consistent with this structure. So we have indeed a protonated backbone, we have a triazolide bound, a triazolide and an acetylide bound. And if we do isotopic labeling, basically we see that the deuteride or the deuterium atom that is in the substrate ends up there, and that is because the proton over here in the transition state is actually on the opposite side of where the L acetylide comes in. So basically we have the surface or the dicopper system, the alkyne comes in and protonates on this side. So the deuterium atom ends up on the bottom of the plane. So here the acetylide is behind the naphthyridine and the deuterium is on the back side, but that triazolide is on the other side of the plane and can only take protons and not the deuterium. And that is indeed what we see. We see 94% proteo triazole, we see 6% differently, and that's again because on the same time scale but quite a lot slower, we have some deuterium exchange, which we also confirmed independently. I'll skip this because it's basically turbocharging the same reaction, but what I would like to focus on is that indeed we can combine metal-metal cooperativity, the cooperative action of multiple copper atoms, to stabilize these various proposed intermediates for the copper catalyzed azide alkyne click reaction, and also use metal ligand cooperativity to make the rate determining step easier. So with that, I would like to end my tale of two coppers for today. And what I hope came across is that copper hydride and copper alkyl species are very dynamic in solution. But using our expanded pincer ligands, we can sort of stop that equilibrium and gain access to mostly well-behaved di-copper systems, enabling us to study the inherent reactivity of di-copper species. And I showed you we can do this also using a combination of metal-metal and metal-ligand cooperativity, in the cooperative hydrogen activation, the click reaction I just showed, and also in the formic acid dehydrogenation reactions, wherein they do display distinct reactivity from monometallic systems, but also that we can mimic clusters with only 2 metals, which is something that I'm really excited about, and something that I hope to gain more insight into the future, is to see if we can actually mimic the intrinsic reactivity of the various cluster facets that we have in larger clusters, and perhaps even go to mimicking heterogeneous catalysts by using well-defined molecular systems. But that is something hopefully for the future, because I first need to get funding to do that research. All right, most important slide. The people that did the work, Cody did the click chemistry, Roel most of the copper hydride chemistry, and Erikos was at the time master student who did most of the ligand development. The click project was also a collective of 4 bachelor students. They were there for a month and all worked together on it. Some colleagues for funding, and of course Felix for working really hard to gain some insight into the copper hydride hydrocyanidation and basically disproving all the mechanisms that we came up with. But it seems to be a bit more complicated than what we think. So that's something that's still to be continued. And last but not least, I would like to thank you for your kind attention. And if you have any questions,